So I have a short bonus for the introductory videos to the paper mache series. It's a little bit of math. It's about curvature, which I will show first in a 2D setting, and then talk about curvature for two-dimensional objects in three-dimensional space, which is relevant to our paper mache constructions. So let's think of how things look in 2 dimensions. We're talking about curvature, so we're talking about curvature of some curve drawn on this piece of paper. And at every point, you could look and you could compare, and you could say, oh, at this point it's curved, but at this point it looks more curved, okay? And then there's a rigorous mathematical way to define what curvature is. So if you look at this point, what you could do is you could draw a circle that fits that, and you could talk about the radius of that circle, and then the curvature is 1 over that radius. And of course, over here, you draw a different circle, right? And the circle that fits is smaller. And so the R over here is smaller, but that means 1 over that R is bigger. And there's one final thing I can say is if you have a curve that has a kink in it, okay? Well, here you could say the curvature is infinite. And if you know any calculus, the way you can make sense of that is if you took this shape and rounded it out just a little bit, then this curvature would be really big because the radius of this little circle is small. And then to get the actual curve that you want, you have to let that smoothing go to 0. And so the curvature is infinite in that case. Now, for objects in three-dimensional space, we're going to look at the surface of the objects and talk about its curvature. I've got this handy demo. And you notice there's kind of 2 things going on here, right? In this one direction, right? There's a straight line. There's no curvature. Curvature is 0, right? But there's another direction, in this direction, where the curvature would be the 1 over the radius of this circle. And what you can show mathematically is every smooth surface. So I'm going to say a surface without kinks. Let's say that there's some deeper mathematics that you need to describe exactly what I mean. But for every smooth surface, at every point, you can always get 2 orthogonal directions where you could have a well-defined curvature in the sense of the 2D curvature that I drew on the piece of paper in the earlier discussion. So, of course, this is a simple case, right, where all the curvature is in one direction and there's none in the other direction. But now you get the idea for surfaces. There's now 2 curvatures. And you can look at, okay, this is going to be a cookie jar eventually. You can talk about the curvature, right, of these flat pieces. Of course, is 0 because it's 0 and it's flat in both directions. But there would be on these corners, you're going to have 0 curvature in one direction, but there is this infinite curvature in the other direction. Our interest, of course, is in covering different shapes with pieces of paper, okay? And you'll notice that for my two demo objects, right, this one I can cover with a piece of paper very easily. And even this one that has infinite curvature, I can cover just by bending the piece of paper over this way. There's a type of surface which can be covered with a flat sheet of paper without wrinkling, and it's called a developable surface. And of course, this is interesting not just for paper mache, but for manufacturing when you're making things out of sheet metal. You want to have shapes that you can, bend your sheet metal into to make those shapes. Okay, so now let's look at the kind of shape that we might want to deal with this bowl, right? So this obviously has the curvatures, right? You got one this way and then one this way. So it's exactly those orthogonal directions where you have curvature defined as in the 2D setting. But this surface, right, which has non-zero curvature in both directions, you cannot put a piece of paper in without it wrinkling, right? Okay, it's got a wrinkle. Okay, so we're going to be coating things with paper and gluing it down with paper mache paste. Wrinkles are not a bad thing. They're a feature, right? You get some texture on your thing. But if we're going to explore this a little bit farther, and we think of the type of curvature is and the piece of paper we're putting in together have a wrinkle factor, right? So for the two shapes that we had before, there's no wrinkle factor. But for this shape, there's a wrinkle factor, and you know this already if you've ever tried to wrap, a basketball up as a gift for someone that you have wrinkles in the wrapping paper. There's no way around it. And so there's two ways that you can reduce the wrinkle factor. One is you can use a smaller piece of paper. Okay, and then I don't know if you can see this, but you can practice this yourself. The wrinkles are less pronounced. Okay, and that's because curvature effects scale like 1 over the size of the object you're trying to put on them. And so if you make the paper half as big, half in both directions, so a quarter of the area, you will reduce the wrinkliness by a factor of 2. Of course, the other thing you can do is you can change the material properties of the paper and make it less wrinkly by getting it wet. Now, in the bowl, I'm going to just use water and not paper mache paste, because this kind of bowl, the paper with paper mache paste will just glue on and not come off. Okay, sorry, I ripped that piece of paper. Let me try again. Okay, I'm just going to wet this piece of paper. And if you do this at home, then you will find, a similar size piece of paper. Now, when you put it in, you can get it to stick down, and there's still some wrinkles. But there's less wrinkling going on than there was before. So there you go. A little bit of mathematics, curvature, developable surfaces. These are all things that you can find on the internet if you want more information about them. Math is fun. Okay, I look forward to seeing you in January for the start of the bowl project.